Let's start today's lecture. So, uh, hello, welcome everyone. Today it's the 10th week of the course NPTEL course de-09 of Control System by Professor S. Shankar Ram. So, in this week, the professor has taught about the bode plot and the nyquist, basics of nyquist. So, the questions this week will mostly focus on bode, and next week it will be more on the nyquist side. So this is a very basic question. In this question, if you understand, then most of the doubts and how to plot the bode diagram and all will be clear to you. Okay. So the question says, consider a negative feedback closed loop system whose open loop transfer function is given as this. Okay, this is the open loop transfer function. So find the closed loop transfer function of the system. So this part is very straightforward. So I think you can solve it like we know if okay, one second. GS HS is the open loop system. Then the closed loop transfer function will be GSHS divided by unit feedback. So 1 plus GSHS. So just quickly calculate. So just quickly calculate the closed loop transfer function. So the open loop transfer function is s plus 1 divided by s square plus 12s plus 20. That means the closed loop transfer function will be just verify this, s plus 1 divided by s square plus 12s plus 20 whole divided by 1 plus s plus 1 divided by s square plus 12s plus 20. So this will turn out to be s plus 1 whole divided by s square plus 13s plus 21. So this is a very basic question, like you have been doing this, like you should have been expert in this uh, closed loop, finding the closed loop transfer functions. So this part of the question is very simple. Next, it asks about the static position error constant. So what do you mean by static position error constant? So our open loop transfer function, I will write it again. It's s plus 1 whole divided by s square plus 12s plus 20. Okay. So what do you mean by the word static? Static means it's not moving. It doesn't have any frequency component. That's why it's static. Like it's not oscillating. It's static. So that's why we can take for the static position error constant. What will be the like if the value limit s tends to 0, which means j omega tends to 0, s plus 1 divided by s square plus 12s plus 20. So what will be the value? Very straightforward. You can directly say what will be the value? Static position error constant. So this will be 1 by 20. Okay, simple. So the first question, the static. Yes. Yes, the static position error constant for the open loop transfer function. Okay, yeah. Static position error is equal to 1 by 20. So what happens if I want to make it in dB scale? So this is in linear scale. So in dB scale, it will be 20 log 20 base 10. Okay. So what will be the value? It's 1 by 20. So I can write 20 log 20 to the power minus 1 base 10, which is minus 20 log 20 log 10 log 20 base 10. Okay, which will be approximately equivalent to negative 26 dB. Okay, you can just verify this. Okay, so next comes in the question, like the static position error constant. We have next plot draw the bode diagram if the given system. Highlight the following attributes. Okay, so we'll highlight the, yeah. Okay, using the closed loop transfer function. Okay, then you just need to verify, like it's the, you know, the closed loop transfer function. This is the closed loop. Then it will be 1 by 21. Okay. Yeah. Yeah. Actually, you are correct. So it should be it's 13s plus 21. So it will be 1 by 21. So you just need to recalculate this thing in dB scale. Okay. If asked in dB scale, otherwise no need. You like in assignment there will be options. Otherwise, in while exam, you can keep it like this also. Then the bode plot. Okay, the bode plot. Just remember this: the bode, nyquist, root locus, everything is done for open loop transfer function, not the closed loop transfer function. Okay, because what do we do in the regular root locus? In root locus, we have a parameter k, the open loop transfer function like k by something something into something something. Okay, we don't know the value of k, so we change the value of k and we'll observe where the poles lie. That is called the root locus, and the root locus diagram we do for open loop. Similarly, the nyquist will also will draw for the open loop plot, and the bode also will draw the open loop, because if we have already have the closed loop transfer function with us, then no need to analyze anything. We just want stability or something, we can directly do like analyze the where the poles lie. So for any like generally we do the mm, word plot for the open loop transfer function, or even the even question, in the question if it's given, find the word plot of the closed loop transfer function of unit feedback, then you need to do the closed loop transfer function. Otherwise, in general, it's for open loop transfer functions. Open loop transfer functions. Okay, then what's the open loop transfer function? It's s plus 1 divided by s square plus 12s plus 20. So the first step in board, what you must do always to avoid any kind of discrepancy or any kind of problem you face, it's called factorization. Okay, factor the transfer function which you are given, factorize it. So if I factorize it, what it will be? S plus 1 divided by s square plus 12s plus 20, sorry, 20 is equal to, I can write s, the numerator as s plus 1, it's already there. What I will do, s plus 10 into s plus 2. Okay, this is the basic factorization I will get. But when doing the bode plot, uh, to avoid any kind of problem in future, what I will do, I will make all the s plus something term as 1. Okay, how? I will take 10 common from this term and 2 common from this term. If instead of s plus a, then I will take a common. So 1 into s plus 1 whole divided by 10 into s by 10 plus 1 into 2 into s by 2 plus 1. Okay. Then what I will get? I will get 1 by 20 s plus 1 into 1 by s by 10 plus 1 into 1 by s by 2 plus 1. Is this part clear? Can you get some yes or no? Is this part clear? Okay. I don't know why. S plus 1. Okay. So now you can see, I will write it in different color. This part is the DC gain. This is the zero part, and these two are the pole. Okay. Now comes the factorization is done. Let's try to plot. Okay. So the factorization is done as 1 by 20 s plus 1, 1 by s by 10 plus 1, 1 by s by 2 plus 1. Okay. Then who can say the corner frequencies? How many corner frequencies are there in this equation, and what are they? Simply whatever is the remaining, like s plus something. Okay, sorry, s, when it's s plus 1, when s plus 1 is there, like plus 1, then whatever is then in the numerator, they are the corner frequencies. In last class, I had explained what is corner frequency, low frequency and high frequency, the meeting point, that is called the corner frequency. Now I am giving you the shortcut. Any question comes, you factorize it like this, and when the plus s divided by something plus 1 is there, then whatever is in the denominator, that will be the corner frequencies. So who can say what are the corner frequencies? It will be s divided by 1 here, so it will be 1, 10 and 2. Is it clear? If this is clear, then I'll go to the next part of drawing the uh, because drawing the bode diagram, it is very important to get what are the corner frequency. Okay, so let's plot the bode. So in bode plot, there are generally two uh, plots. One is the magnitude plot and another is called the phase plot. Okay. Let's draw one by one. So what happens, uh, for magnitude and phase plot, I can do individually calculate the plots for all the four terms, 1 by 20, s plus 1, and I will add them. This is the very basic board plot diagram, how you can make approximate board plot diagram. So I will just draw. Okay. So one question I want to ask, there are three students in the lobby, Agam, Ishan, and Hoishal. So can you tell what can be this frequency? Because this is in omega. Okay, this is a logarithmic omega. So log omega, maybe I will write log omega, and this is in dB. Okay, what will be this frequency? Will it be 0 or 1 or 5 or 10? What it will be? What can be or what cannot be this frequency? What starting frequency? Ishan, would you like to answer this, or Hoysal, or Agam? Anyone? Okay. Ishan says, sir, this cannot be 0 in log scale. Okay. So, exactly. This can be anything but 0. Okay. So, I can make it as 2, 3, 5, anything what I want, but this cannot be 0 in a logarithmic scale. I am saying it's a log scale. Okay. So anything I can take. So I will take at very low, like less frequency initially, 0.01. Then this point, this point, this point, this point. So this will be 0.1, this will be 1, this will be 10, this will be 100, and this will be 1000. Is it clear? Because it's a log scale, the units will be multiplied by 10. Okay. And suppose I will make a smaller black. Suppose this is the 0 dB line, 0 dB, and maybe this. Okay, and this is minus 20, minus 20. Here this is plus 20. Okay, and like that. Okay, so in dB scale. So what will be the what is the dB for this the diagram for this component? 1 by 20, 1 by 20 in the dB scale we had calculated, it was around minus 26 dB. So I will straightforward plot it as minus 26, so somewhere around this, and it will be straight. Okay, very simple, because this plot is for 1 by 20. So next for S plus 1, okay, its corner frequency is at 1. So, let's try to analyze S plus 1. So we can write it j omega plus 1. So for lower frequencies, before the corner frequency is 1. So before the corner frequency, what about the lower frequency part? It will be almost approximated as 1, which means the dB scale is equal to 0 dB. But in high frequency, this will be omega. Okay, and this will be like accordingly log 20 log omega dB. Okay, this is clear. This part is, that's why before 1, before coming to 1, this frequency will be 0, and after 1 it will be going with 20 dB per decade. Okay, this, yes, it's 20 dB per decade. What about the term S by 10 plus 1? This I can write at j omega by 10 plus 1. So similarly, at lower frequency level, it will be 0 dB, and for higher, it will be accordingly omega. But the corner frequency, sorry, it will be negative omega because it's 1 by. Okay, so it will be negative omega. So that means the plot, I will choose some other color. It will go up to 10 at 0 dB. Then from 0, it will go with negative 20 dB per decade. Okay. So what I am doing is, I have factorized the transfer function into 4 parts. One is this part, this part, this part, and this part. I am individually plotting the magnitude plot for all of these. Okay. So for this part, it is minus 26 dB constant. It doesn't change irrespective of any frequency. At 0 frequency also, this is minus 1 by 20. At 1000 kilohertz also, it doesn't affected by any frequency. What happens with S plus 1? In in the last class, I have explained in frequency response, we generally analyze with two frequencies. One is low frequency and another is high frequency. And their meeting point is called Agam. What is exactly? So what is the corner frequency of S plus 1? 1 omega. Okay. So at 1 omega, the lower frequency and higher frequency will meet. So j omega plus 1. S I can write j omega. So at lower frequency, when the frequency is low, omega is very less than 1 is equal to 1. What will be the value? I can approximate it as 1. Am I correct? So this will be 0 dB in dB scale. Okay. And what about in high frequency? Omega. So in dB scale, it will be 20 log omega dB. So when my logarithmic scale is there, so this will be at 20 dB per decade. 20 dB per decade. Per decade. Decade means 10. Like here we are analyzing for 10 multiple, na? 10 times multiple. Yes. So that's why it's a positive. And what happens when I am analyzing this part? It is 1 by S by 10 plus 1. The corner frequency is at 10 omega. So that's why till 10 omega, 0 for low frequency, it's 0 dB. After that, it's negative omega, negative 20 dB per decade. Understood? And Ishan and Harshal, is it clear to you guys both? Okay, very good. Now you guys tell me what about this 1 by S by 2 plus 1? How the plot will be? The corner frequency is at 2. Okay. And so I will write it 1 by S by 2 plus 1. So it will be 1 by j omega by 2 plus 1. So at low frequency, it will be simply 0 dB again because 1 by 1. And at high it will be negative omega. Okay, very simple. Then what happens? I will check some other color, orange maybe. So 2 will be somewhere around here. So this plot will come to this. Then it will go with, sorry, this part, no, negative, with this, like this. Okay. So now I have all my 3 plots. Now let's try to plot the actual bode diagram. Okay. So I will draw it here. So 0.01, this is 0.1, this is 1, this is 10, this is 100, this is 1000. Okay. So till this point, I want all of your attention. Till point 1, this point, everything was 0, but this was minus 26 dB. Okay. I will write it as minus 26, minus 26. Okay. Then till 1, I can write it was minus 26 dB, minus 26. Okay. After that, from 1 to 2, the orange was 0, but the green was increasing. So I can plot like this. Okay. Then from 2, this point 2 to 10, this was increasing with 20 dB and this was decreasing with 20 dB. So they cancel each other out and this will be kind of a straight line till 10 dB. Okay. Then after 10, 10, 10, it will be again this purple color will come. So that's why it will go with negative 20 dB per decade. Is it clear? Is it clear? The magnitude, how it's done? Can you just type in chat if yes or no? Okay. For 1 to 10, okay. Then up to 1, it was minus 26. From 1 to 2, 1 to 10, I will divide as 1 to 10, I will divide as 1 to 2, then 2 to 10. Okay. So 1 to 2, the black curve remained as it is. The green curve up to 1, it was 0. After that, it was increasing 1 to 2. The orange curve was 0 and the purple curve was 0. So straightforward, minus 26 plus whatever the green curve was contributing. Clear? 1 to 2, no doubt. The problems comes with 2 to 10. So what I want you guys to imagine, from 2 to 10, the green curve is increasing with plus 20 dB per decade, and the orange curve was decreasing with 20 dB per decade. Okay, one is increasing with a magnitude like rate, and another is decreasing with the same rate. So that's why from 2 to 10 they will cancel each other out, and the value, the magnitude will remain constant. Is it clear now? You can take some example also, like take like some 5 or 6 some value, and as you take the magnitudes here, then take around 7 or 8, you will find it has the same magnitude. Is it clear, Agam? So after 10, another minus 20 dB per decade comes. So it was constant, then it decreased. So for to plot it for a shortcut, now it comes how to draw shortcut. First step is you need to factorize anyhow, then find the corner frequencies, mark the corner frequency, mark the corner frequency 1, 2 and 10. Okay, so for the DC gain, for starting from like this y-axis to first corner frequency, draw it straight line. After that, at the first corner frequency, if there is a 0, there will be an increase of 20 dB per decade, or if it's a pole, it will be a negative 20 dB per decade. Then at the second corner frequency, the next corner frequency, if there is another pole, another 0, it will be again plus 20. So initially it was 20 plus 20 dB. So then another 0, that means it will be 40 dB per decade. If there is a 0, if there is a pole, then it was plus 20 dB, and 0 will introduce minus 20 dB. That's why it was straight line. After then the third corner frequency, you were introduced with another pole. That's why negative 20 dB per decade. So identify the corner frequencies. Just know whether there is a pole or 0 at that point. So whenever the pole is there, negative 20 dB. When 0 is there, positive 20 dB. Simple. Bode diagram is that simple. So now, is it clear? The magnitude plot. I will go to the phase plot. Okay. Ishan has a doubt. Sir, I have a doubt. In the second and third term, we have a slope at minus omega. How did you know the x-intercept in the second plot of the first uh, graph? Second plot of the first graph. Do you mean the green curve? Yeah, I can hear you. Okay, the intercepts means yeah. No, we don't need to find them because they has the look. simple graph theory, simple XY plotting. You know the y is equal to mx plus c, right? So once you get to know the m, and once you have any point, you have one point and you know the m. So I will say at 5, like the point is 1 comma 1, okay, 1 comma 1. At 1 comma 1 I want a slope of 45 degree. So how many lines you can imagine? There is only one, right? Only one, like this is the m, fixed m. So what similar thing, just imagine in our diagram, okay? You know the corner frequencies, okay? The corner frequencies at 1, at 2, and at 10. You know at this point there will be a positive 20 dB per decade slope, okay? And I don't care what is the this intercept. I don't care. I know the corner frequency and I know the slope. That's it to plot a diagram. Similarly, for at 2, I know the corner frequency. I know that it's as it's a pole, there will be a negative 20 dB per decade. I will draw a negative 20 dB per decade. Again, at 10, a negative 20 dB per decade. Is it clear? Yes. So we don't know the x-intercepts. We know one point and we know the slope. That's how we are plotting the diagram. Huh. And be careful here. There are simple poles. That's why we are doing negative 20 dB per decade. If there are the poles are s square plus 1 or s square by 10 plus 2, then there will be negative 40 dB per decade. Okay, that you will know in the next class, maybe next lectures. Okay. So is it clear? The bode magnitude diagram, you can like plot any kind of questions involving simple poles and simple zeros, I think. So if this part is done, I will go to the phase diagram. Is it clear? Okay, I'll assume it is clear. Okay. So I'll just erase this thing. So the phase similar plot, I have like for omega is equal to 0.001. Sorry, 0.001 is too much. So let's make it 0.01, 0.1, 1, 10, 100, 1000. Okay. So for phase, we have three references mainly. One is 0 degree, another is positive 90 degree, and the third is negative 90 degree. Mind it, these are for simple poles. That's why I'm only considering positive 90 degree or negative 90 degree. If there are the multiple poles like s square or s cube terms, so the multiples of 90s will appear. Okay. So, okay, I'll write down the expression again. It was 1 by 20 s plus 1 s by, sorry, 1 by s by 10. 1 by s by 10 plus 1 shit. 1 by s by 2 plus 1. Okay. So similarly, I will draw the phase diagram for individual. So what will be the phase contribution of this term? 1 by 20. What will be the phase contribution? Somebody can just say. Very good. Because it doesn't have any j omega term. So when it doesn't have a j omega term, a plus jb, so tan inverse b by a, so it's b is 0, that's why it's 0. Okay, you can like calculate like this also. So this is for 1 by 20. Okay. So what about s plus 1? Now comes s plus 1. S plus 1, I can write it as 1 plus j omega. Okay. So when I write it as 1 plus j omega, then the corner frequency is at 1, and at the corner frequency, what is the angle? Tan inverse omega by 1. So at corner frequency, it will be tan inverse 1, which is 45 degree. Correct? So at 1, it will, I'll choose some other color. Red. The 45 will be here. So this. I'll just put it like that. Next, at omega tends to 0, like that means lower frequency. I know I have repeatedly said lower frequency, higher frequency, corner frequency. These three are most important. For lower frequency, what is the uh, tan inverse? It will be 0. Tan inverse of 1, sorry, 0 by 1. So it will be 0 degree. So, and for high frequency, omega tends to infinite, it's tan inverse infinite, which is positive 90 degree. Okay, clear? That means for low frequency, it will be 0, then it will come to this, and it will finally settle at 90 degree for any high frequency. This diagram is clear to everybody? This is for S plus 1. Then similarly, erase this part. Similarly, 1 by S by 10 plus 1. For this, what is the corner frequency? The corner frequency is at 10. Okay. So at the corner frequency, what is the, okay, I'll just j omega by 10 plus 1. Okay. So the magnitude, it will be tan inverse, so negative tan inverse j omega by, like j omega by 10 whole divided by 1. Okay. Because negative is there because it's in denominator. Okay. Then at omega is equal to 10, what is the angle? It is minus 45 degree. Is it clear? So it will be, this is 45, this is negative 45. So this will come like this point. Similar low frequency. Tell me what is the low frequency like phase when omega tends to 0, it will be 0 degree, and when omega tends to infinite, it will be negative tan inverse of infinite, which is negative 90 degree. Clear? So that's why it will start from 0, it will be almost like this somewhere, and this is 1 by s by 10 plus 1. So bode plots are kind of, we can say, approximate diagrams. That's why it's like we can approximate to 3 points: initial, corner frequency, and final. So these are approximate. I don't say these are exact bode diagram. These are approximate bode diagrams. Okay, frequency, approximate frequency responses. Okay, now I'll choose this color. Okay, so now comes, okay, 1 by s by 2 plus 1. Similar, what I had done, j omega by 2 plus 1. That means the angle will be tan inverse, angle will be negative tan inverse of j omega by 2 whole divided by 1. So the corner frequency is 2, so it will be, the angle will be negative 45 degree. Okay, so at 2, this is 2, like this, and omega tends to 0, it's 0 degree. Omega tends to infinite, it's negative 90 degree, just like the previous one. So this will be like this and going like this. Okay, this part is clear, this diagrams, body diagram, and now we'll just add them up. Okay, all, and when we add them up, they will be like where I'll draw, maybe in this diagram only. I'll choose green color for the main diagram, so you can just add it and see. Okay, simply for each diagram. So this part is clear to everybody, the body diagram. Okay. Yes, so the steps, first you need to uh, do, what you need to first do is factorize it, then for individual draw the plot the magnitude diagram, and for then the approximate magnitude diagram, then the board plot for the phase diagram. Okay, also you can verify is, what you can do is, the corner frequencies, the corner frequencies are omega is equal to 1, 2 and 10. You can do is, when you are in exams, like in your college exams, if the question is asked, you will be provided by a graph sheet, logarithmic graph sheet, and you need to plot this. So take some omega. First, omega is equal to 0.01 or 1. Okay, 0.1. Then omega is equal to 1, omega is equal to 2, and omega is equal to 10. These three corner frequencies. Then maybe omega is equal to 100. Okay, plot for these 5 diagrams. Okay, you have this these 4 plots. Then for giving the individual points somewhere like this, you will get the approximate diagram like this. So this is very straightforward. So, and the time is also there. So I'll just briefly tell you about the Nyquist plot. So the bode plot is clear to everybody, I guess. So now moving to the Nyquist plot. So the what a Nyquist plot is, in bode diagram, what we do, there is a omega axis, then is a magnitude axis, magnitude, and we do, there is a omega axis and there is a phase axis. Okay, but in this Nyquist, what we do, we have, in the same plot we will have both the magnitude and phase. This will be in S plane, so this is purely real part and imaginary part, and for different omegas where the plots will be, we'll see. Okay, so I hope you have gone through the lectures, because I am not going to go deep into the Nyquist, and Nyquist is very important. I'm telling you, Nyquist is very important. Be careful, listen to the lectures carefully, you'll understand. So before going to these two, I'll just ask, like, so remember, okay, this will always help you. This is kind of the shortcut which generally I give in the class. This will, this is real axis, this is imaginary axis. So about the phase, this is positive 0, this is negative 0. This is for remembering and like how to draw plot everything correctly. Okay, there is no hard and fast rule for this. This part, like, I'll tell, this is positive 90 degree, this is positive 180 degree, and this is positive 270 degrees, and this is negative 90 degree, negative 180 degree, and negative 90 degree. Sorry, negative 270 degree. My bad. Negative 270 degree. So when you will draw any Nyquist plot in the future also, when the plot omega tends to infinite, it's converging at negative 90 degree. So you must close it like this, not from this. Okay, because this side is the negative 90 degree. Remember this plot positive 0 negative 0. So when the uh, there is the like at omega tends to infinite, when it's called at negative 0, it like you will know. So this plot must be like this. If it's a positive 0, it should be like this. Okay, so you will know these things in the next class. So now coming back to our question. Okay, so draw the Nyquist plot for 1 by s plus 4. Okay, let's try to analyze what I have taught in the class till now. So 1 by j omega plus 4. So I want in real and imaginary. That's why I will segregate it into real and imaginary. What I will do, I will multiply j omega 4 minus j omega and like 4 minus j omega into 4 plus j omega. Okay, so what it will be? 4 divided by 16 plus omega square. Okay, and this will be minus j omega divided by 16 plus omega square. Sorry, it will be negative omega square. My bad. Okay, uh, you understood how I divided into uh, real and imaginary part? This. Huh. So now what I will do, I know in frequency, what you will do always 2 points, low frequency, high frequency. So when omega tends to 0, okay, okay, I will write. So this has the magnitude. The magnitude I can write as root over of 4 by 16 minus omega square whole square plus omega divided by 16 minus omega square whole square, and the phase will be negative tan inverse of omega divided by 4. So this part is clear. So then when omega tends to 0, tell me the magnitude and phase. So what will be the magnitude when omega tends to 0? Quickly, somebody. Check it again. 1 by 4. You need to check it again. Yes. And phase. What is the phase? Omega tends to 0. It's 0 degree. Okay. That means we have the magnitude for omega is equal to 0. We have a magnitude like this point. This is 1 by 4 and at 0 degree. Okay. For omega tends to infinite, what will be the magnitude? The magnitude will be tell 0. Okay. And remember, Nyquist is not in dB scale. It's in normal scale. Phase. Tell me the phase. What will be the phase? Very good. Minus 90. So now tell me. So it should be completed from this, or it should be come from this, like this or like this. Which one is correct? Yes, exactly. That's why, because if you don't remember like this, you will face, like, you will get it wrong. So it is like this. Okay, and this is at 0 for omega is equal to negative. So the, the for Nyquist plot, actually you have for the other side also. I'm not drawing the other side. So the question says radii in the, what is the radius? This will be half, and this is also, you can verify, this is also half this length. So the radius is half for this. Okay, this is 1 by 4. Oh, sorry, this is 1 by 4, then this will be 1 by 8 na? 1 by 8, my bad. Okay, so next comes s plus 2 divided by s plus 10. Yes, so simple, j omega plus 2 divided by j omega plus 10, which is equal to j omega plus 2 whole into 10 minus j omega divided by 10 minus j omega into 10 plus j omega, which is equal to, the numerator is omega square plus 20 and 10 minus 2 plus 8 j omega whole divided by 100 plus omega square. So the real part will be 20 plus omega square whole divided by 100 plus omega square plus j 8 omega whole divided by 100 plus omega square. So the magnitude will be root over 20 plus omega square whole divided by 100 plus omega square whole square plus 8 omega divided by 100 plus omega square whole square. And the phase is equal to tan inverse of 8 omega divided by 20 omega, 20 plus omega square. Okay, so now let's draw the bode, sorry, Nyquist. Okay, so for omega tends to 0, okay, tell me the magnitude. What is the magnitude? Omega tends to 0. Again, calculate again. Little bit wrong. Yes, exactly. So it will be 0.2 for omega is equal to 0. Then 0, and the angle is, it's 0 degree. Okay. So for omega tends to infinite, calculate it. What is the magnitude for omega tends to infinite? So for omega tends to infinite, it will be 20 plus omega square divided by 100 plus omega square. So it's infinite by infinite. So you need to take the L'Hopital rule. So it will be, first derivative will be 2 omega divided by 2 omega. So I differentiated with respect to omega. So this will be 1. Okay. So and what about the angle? Tell me the angle. It's again infinite by infinite. Calculate it again. Calculate it again. Are you sure? Minus 45. It will be the phase. Tan inverse of 8 omega divided by 20 plus omega square. So it's again omega by omega. So the first derivative I will take. So it will be 8 divided by 2 omega. So the omega tends to infinite. It's coming tan inverse 0. Did you understand this part? Yes. So it will be 0 degree. So this will be for omega tends to infinite. It is at 1. So the diagram will be like this. It's coming to this. So in the center, you can verify this radius is also zero point 0.4 because this is also 0.4. So the question in the red eye, this is 0.4. Okay, and the like actual full diagram is will be like this, and for this it will be again. So I think like this was a very simple question. So I hope you have understood both the questions today. Yes, sir. Yes, Agam. Sorry, Ishan. Because last time there was a problem in the video. I don't know why. The video was like freeze, like the video frame was freezing. So I tried to rectify it again and again. That's why I uploaded it a bit late. Otherwise, I generally upload it by tonight only. Okay. I'll try to upload it by tonight. Yeah. Thank you very much. So have a great week ahead. Happy Dasera. Bye. Thank you.